All right. Good afternoon, everyone. My name is Rahman Azari. I'm an associate professor of architecture, and I also run Resource and Energy Efficiency Lab in Department of Architecture, RE2 Lab. I'm presenting DECODE, Digital Twin Environments for Comprehensive Decarbonization Evaluation of the Urban and Rural Real Estate. And this project is an amazing collaboration between PIs from architecture, Professor Iulo from mechanical engineering, Professor Fitzsimons and Guimaraes, and from architecture engineering, Professor Julian Wang, and two wonderful PhD students, Hanin Othman and Shuji Liu, which I would like to ask them to raise their hands because they were the main driving force behind actual doing of this project. I just did all the talk. This project focuses on digital twin. And digital twin is a digital model replica of an actual physical environment, and it's different than digital shadow in the sense that digital twin is able to provide bi-directional data exchange between the physical environment and the digital model, in the sense that we would be able to collect data from physical environments through sensing, but we would be able, within the digital twin environment, being able to do prediction, simulation, data analytics, and providing some sort of decision support system in order to lead to certain changes in the physical system. While digital shadow is only able to provide one directional or unidirectional data exchange between physical system and the digital model. So the knowledge gaps that exist is that we all the time do sensing, we do simulation, we do analytics, but all of these are done in a fragmented manner. So we wanted to create a technologically integrated framework to be able to do sensing, simulation, prediction, and decision support all in one environment and create complete feedback loops. So the idea of this project was how we could design, develop, and validate digital twin environments based on IoT sensing and create, as I said, a technologically integrated platform and propose adaptation pathways for climate risk mitigation in the built environment. So the environment, the digital twin environment that we created consists of 4 components. The first is urban mapping, second is environmental sensing, simulation and analytics, and fourth, visualization. Again, I emphasize the novelty of this project is that we do all of these 4 in one technologically integrated environment. Starting with urban mapping, we were able to create an environment that you give an address, any address, and we would be able to look up the model in that address, the building in that address. There is a 3D model of that building in the address, and we would be able to extract data from publicly available data sources, and all of these building and property data would be attached to the 3D model of that building, which again could be any building. In this case, this is the Stuckman family building, which houses Hamer Center and Department of Architecture and School of Architecture and Landscape Architecture at Penn State. So this is the building here right across from the water tower that you see. When you click on this building, you would be able to see the 3D model of it. You would be able to see all of the characteristics of this building, from the type of the building, educational in this case, to number of floors, to all of these, the other data that is out there that is available. Again, we're not inventing this data. Data is out there. We're just integrating them and making them attached to this 3D model of the building. And this is done in a Rhino and Grasshopper environment and through attachment of the data within Grasshopper. We also would be able, through some external tools that are attached and integrated into this platform, we would be able to see the weather data related to any location that has publicly available Department of Energy weather data. In this case, you could search for a state college, find the weather station in a state college, and see all of the weather data, historical weather data related to a state college. The second component of this project was environmental sensing, and this is primarily the work that Hanin is doing as part of her PhD project. And So Hanin has been developing some low-cost Raspberry Pi multi-sensing systems for indoor air quality that would measure CO2 temperature, relative humidity, VOC, PM, and illumination. And these low-cost sensors has been calibrated, compared with the actual high-cost sensors, and then we have deployed these sensors within Hamer Center in the Stuckmann School of Architecture and Landscape Architecture. And then we also, in addition to fixed sensors, we attach them to some robotic sensors that would be able to go through the interior spaces and collect the indoor air quality data, and we would be able to see in real time the data, what type of data is collected, where is the location of the robot. The robot is able to provide a map of the interior space as well, and we would be able to see what data and in what ways those data fluctuate with regard to indoor air quality. So we collected a lot of data. We combined fixed sensors with mobile sensors that are installed on robotic devices. The idea was that how we could use little data that we could collect from all of these sources to create maximum spatial resolution for indoor air quality. In other words, with a limited number of sensors, how we could best predict the indoor air quality in an architectural space. Our next plan is to deploy this robot into outdoor environments in order to be able to collect more high-resolution air quality and outdoor thermal comfort data from outdoor spaces across the campus. What we have been doing in the third component of this digital twin, which is simulation and analytics, we are able to monitor in real time all of these data that I just showed you in the previous steps. And then we would be able to show this data not only in 2D, but also spatially connected models as well. Again, the data would be CO2, temperature, relative humidity, VOC, and so many other types of data that could potentially be sensed and collected. And then, as I said, we want to use this data in order to predict the parts of the building and parts of the outdoor areas that we would not be able to sense, because you don't have all the sensors, or having all the sensors to deploy would be a very costly experiment. So we want to use a minimum amount of sensors in order to predict the maximum spatial coverage. And these are some of the heat maps that Hanin has been producing to show that how we could generate basically the spatial maps under various scenarios. Starting, for example, this is the same space. The green here is Hamer Center for Community Design in the Stuckmann family building. And in one scenario, we collected data only with one fixed sensor. The second scenario was 3 fixed sensors. And then the third was 3 fixed sensors plus one mobile, one robotic run that would go into the space and collect data. And the fourth scenario was 3 fixed sensors plus 3 mobile sensing runs in order to collect data. And of course, the more sensors that you would have and the more mobile sensing runs that you would have, you would be able to provide better spatial coverage of indoor air quality. And these are all great experiments that Hanin has been doing. Hanin has a poster, and feel free to stop by her posters if you had specific data, specific questions regarding the data that she has collected. And we would be able to also run simulation of the energy performance of the buildings. For now, we focused on 21 randomly selected buildings across the campus and try to analyze the energy performance of these buildings. So within the Grasshopper and Rhino environment, we collect data, we simulate the energy performance of these buildings, and within that platform, we would be able to basically present these results and visualize the results within one integrated platform. So these are some of the results that, based on the simulation of energy performance of these 21 buildings, we are able to present. The results vary from energy use intensity to embodied carbon to operational carbon intensity, so to cumulative carbon intensity. So all of these rich metrics and rich data that would be able to be presented to a facility manager or the decision maker within the university or within a city in order to improve the certain performance of the building. And we did that also under various scenarios of retrofitting and passive house construction. So for example, what if that these 21 buildings within Penn State wanted to become somehow passive house certified buildings. Passive house is a standard for net zero energy buildings. What if that we wanted to make all of these 21 buildings passive house? How much savings would be associated with the energy consumption? How much savings in embodied carbon, operational carbon, and potentially operational cost could be saved? So we would be able to simulate all of those. We have done it for these 21 buildings. And what if that we would be able to add PV panels to these buildings as well, and how much energy we would be able to generate through those buildings with the passive house scenario, with the PV panels added on their rooftops. And the fourth and last component of this digital twin environment is visualization. So we wanted to enable the decision maker and the user of this digital twin to be able to go through the environment, experience the environment, and see the results. So this is Shuji with the headset she has tried to create a virtual reality environment where you could explore, go through the Penn State. This is our, of course, work in progress. We're still improving the resolution of these spaces. This is a Stuckman family building, so we would be able to go within the environment and see the results of the energy consumption and all of this simulation and environmental sensing data that we have conducted in the previous stage. So basically, you could click on any of those buildings to see the building information, property, characteristics, and see even the energy simulation results. These are different scenarios that you could see that the building has been simulated under which you could choose, for example, passive house to see how much energy saving is caused because of adopting the passive house certification, and all other cool things that has been done by our amazing students in this project. Right. So, okay. Our future work, as I said, this is still a work in progress. We want to make that integration better and more high resolution, so we're still working on that. How we could somehow use the data that we're collecting with regard to air quality, with regard to weather data, integrated as part of our energy simulation. So that is one of the things that we're still working. We want to, for now, the pilot test of this project has focused on part of the campus. We would like to increase the scale of this project to a state college and see what opportunities exist. If, for example, in a state college, if we want to do retrofitting, where we should focus on, which neighborhoods have the highest potential to focus on. And then if we retrofit those houses within a certain neighborhood, what is the consequence? What is the effects in terms of energy savings and embodied carbon savings? How much material would be involved? How much embodied carbon would be saved? And so many other things that we plan to do. So thank you so much.
So I have a comment and a question. So when I saw those 21 buildings and I saw the difference, what you're really saying is, where can I get the bang for my buck with my energy investment? If I'm going to select a building to spend some money on, which building is going to give me the best return? The least amount of dollars for the greatest impact, reduction of energy. So how can you go back to those 21 buildings, let's say, that's the example, that's your database, and rate them and give them some sort of a common sense rating that says, here's where you spend your money first, here's where you spend it second, and here's where maybe you don't get much of a return. Maybe you'd let that go for now until we have better technology or better systems. Like, how do you turn that data, you're almost there, into an implementable tool that the owner can use right away?
Exactly. So thank you so much for the great question. I think that is the one of the goals of the project in the next steps. We want, as you suggested, we want to see not only under various scenarios what could be done, but also for, as you said, what are the hottest spots for energy consumption and carbon emissions. And once we selected those buildings under what specific strategies we could achieve the maximum energy savings and maximum utility bill savings. So that is our objective in this project in the next steps.
Excellent.
Yes.
Thanks.
Thank you.
Thank you. I really loved the presentation. I have a question. You talked about indoor air quality and in conjunction with energy savings. But I remember not too long ago, indoor air quality talked a lot about pathogens going through the air. And I'm wondering if you are thinking of linking some of this research to that question of airflow and building these pathogens. I mean, there was a lot of chatter, I remember, during the pandemic about the dangers of HVAC systems, ventilation, things like that, exposing us to pathogens. Is there any aspect of that that this could be linked with?
Absolutely. So when we do the energy simulation, we are able to control air infiltration, or we call it air change per hour. Oftentimes in energy efficient buildings, you reduce the air infiltration from the outside to the inside at the expense of lower indoor air quality. But the way that we address that low indoor air quality is to maximize or optimize, in a way, mechanical ventilation. But if you do mechanical ventilation, then you're increasing the energy consumption of the building. So there's always this dichotomy between energy efficiency and improved indoor air quality. So you have to meet the minimum requirements with regard to indoor air quality. That is done through energy simulation. So you would be able to basically control the air change per hour within the simulation environment. But then based on those assumptions, what would be your energy consumption? I want to keep, for example, air change per hour in this room at a certain level that is determined by the code. Based on that minimum, what would be the energy efficiency and the energy consumption of my building? That is done through simulation. Yeah. Yes, please.
Was there any thought given to like sensor arrays that we see on mechanical equipment and things like that? So from a construction standpoint, a lot of the pieces of equipment we put in will have sensor arrays in them that we can tap into. So output temperature, input temperature, all of those kind of things. Do you have anything in your research so far that kind of taps into that?
Sorry, I didn't understand that part. The sensors related to what mechanical equipment?
So like your VAVs, all your equipment, your air handlers and
Sure.
stuff like that. Do you have anything that ties that information into the research?
Great question. We haven't done that, but if you think in an ideal world, there would be a lot of sensors deployed in every building, in campus, and in the entire city that you would be, potentially they would be integrated in a certain centralized place that you would be able to connect them. So the capacity technologically exists, but we have not done that. We have not gone to that realm. Great suggestion. Thank you so much.